Hello everyone and welcome back to a new session. In today's session, I would like to go over chapter 18 as a review and do a coding lab in front of you so that you practice its concepts. So I have this lab in front of me and it says write a class called myList that behaves like a forward linked list. This class should include a struct object that represents a node. Each node stores a double value, a head member variable, which is a pointer to the starting node, or null if the list is empty. In addition to those member variables, or to that struct, the list should have functions that operate on this data. So we need an append function, push front, delete node, delete node. So this delete node will delete a value, and this delete node will delete a specific position. Insert double value at a specific position, display node at specific position, display the entire list, and finally destroy the entire list. Notes, be careful about incoming position values that are invalid, for example, negative values, where your message should throw a string error. Assume position 0 is the first node in the list. So let's go over and start with this. Each node should store a double value. So I'm going to start with this section where I have a struct. I'm going to call it my node. This my node has a double mData, and it has a node pointer called next. As a matter of fact, I can right away build a constructor for this. So I'm going to say double a data, and this constructor sets data to be equal to a data, and next to be null ptr. So this is my struct. It's a simple struct. It always have an next because it's a node in a linked list. And in this case, it carries a double variable. And I have a constructor just so we can make it easier to create instances from this struct. The next thing is to actually put these in place. So let's go ahead and say I need a class called myList. This class has a private section. It has a public section. In the private section, I only need a my node head, my node pointer. What else? I actually don't need anything as private in this list. And then in the public section, first things first, I need a constructor. I need do I need an well, I'm not gonna do an overloaded constructor because we are not gonna create a linked list in main and then create an instance based on that instance. I'm just gonna keep it as default because we're gonna create an empty list and then use the functions to operate on that list. So what were the functions? The functions were, let me copy. I think it's better to do that. So copy paste. We have an append, we have push front, we have delete node, we have delete node, we have insert, we have display node, we have display list, we have destroy list. So semicolon, semicolon. So append, when I append, I'm gonna return void. When I push front, it's gonna be similar to append. When I delete node, it's gonna be void. Oops. Same void insert. Same void display void. Display value is gonna be void because it will display, not return. Same, same. Okay, so it seems like all of them are voided. As a matter of fact, I can put a destructor called my list, and inside this destructor I can call destroy list, because that's what a destructor does. Anyway, these are what I need to implement. So I'm gonna start with the implementation here. The first thing is the constructor. Oops. My list. This constructor is default and it sets mhead to be null ptr. Yep. So the next thing is append. So I need to append a double value, meaning my list, it's a void, my list colon, my list, it receives a double. This keyboard, a value. So I receive a double. When I receive a double, the first thing I'm gonna do is create a new node and carry that double. So I'm gonna say I need a my node, L new node equals new node or new my node. And then I'm gonna give it the a value. So now that I have, why it doesn't like this? Not a void function matches the specified type. Void double. Oh, it's not my list, it's append. So this is a pointer. New node is a pointer to a node. This will make it easier to assign next later. So now that I have my list, my node in place, the new node in place, as I mentioned, the first thing to do is grab a copy of mhead in order to operate on it without losing the real head. So I'm gonna grab a copy, my node asterisk. I'm gonna say L current node equals mhead. In append, if I want to think of append, I might have one of two cases. The first case is the list is empty, and the other case is the list is not empty. The list is not empty. It's either empty or not. How do I detect emptiness in a linked list? I simply check if mhead equals, well, in this case, I'll current node because I need to operate. It's a good habit to start adapting to current node instead of mhead after this step. Right when I grab a copy, then I should stop touching mhead, right? So al current node, if al current node is actually null pointer, that means the list is empty. Otherwise, it's not empty. So it's either empty or not empty. If the list is empty, let me open, do I have the whiteboard here? Whiteboard, let's see. Need me to sign in. Sign in. Um, okay. Okay. So in this case, mhead is null. So the fact that mhead is null, then I'm gonna say simply mhead becomes the new node. What is the new node in this case? The new node is a node, loose node, that points to null and is carrying the value right here. This is the new node. If the list is empty, then mhead becomes the new node. L new node. Otherwise, if the list is not empty, that means at some point we added node. So let's assume it looks like this. This is my linked list. And then the last one points to null. So what I need to do is I need to traverse, right? Traverse up until I reach the end. Once I reach the end, I'm gonna then say to the last node to, instead of pointing to null, point to a new node. And the new node eventually points to null. So let's go ahead and do that. So the first thing is I need to traverse. So the first thing is traverse the list till the end. So while L current node M next is not null. So as long as M next is not null, I need to keep moving forward. So L current node becomes L current node M next. This will iterate up until the end. Once I break out of the loop, that means I will be on this node. So it's gonna start at this node and it's gonna check, hey, is your next null? No. Okay, then now I'm on this node. Hey, is your next null? Null pointer, sorry. No, it's not null pointer. Okay, move forward. Hey, is your next null? And it's gonna say, yes, my next is null. So I'm gonna break out of the loop. So when I break out of the loop, L current node is the last node. So I'm gonna tell last node to stop pointing at null and point to the new node, meaning, hey, L current node, your M next is now the new node. So I appended uh, the node to the list. So let's test this part alone and move on to push front. So here it says, below you will find a driver program that you could use to exercise and test your class. Perfect. So I'm gonna grab the append section, copy, paste. So this code is simple. It creates a local instance from the list, my list, and then appends 1, 2, 3, 4, 5 nodes, each with a double value. Append 5 nodes to the list. Okay, perfect. So I'm gonna stop here and then I'm gonna run my program. Error. Mm, Strange. What is the error? Huh, strange. What does it not like? Public void, my list, destroy list. Reference in function, my list. Yeah, why not? It shouldn't care. Oh, because I'm calling it and the definition I think is not there yet. That's why it doesn't like it. Okay. It's still a prototype. There is no definition for destroy list, so it didn't like it. Okay, I appended 5 nodes. Let's see. So my list has an M head. This M head is carrying 2055, which is correct. Here it is, the first one. Let's actually add it to a quick watch, and then I can do this. So mhead is carrying 20.55, and then mnext. Mnext up until null. So let's do this. So 2055 correct, 2.85 correct, 8542 correct, 6128 correct, 41 and 10 9, which is like 11, 110 basically. And then the last one is mnext is null. So notice mnext is null. So here are my five nodes, meaning my append works. Then I can move on to push node. So again, void my list push front, and push front takes double a value. This should be straightforward really, because let's go back to our drawing. Again, I have one of two cases. I'm gonna have one of the two cases. The list is either empty or not empty. And the code is asking me to push front. That means the new node should go in front, and these will come following the new node. So push front. But similar to append, I need to do similar to append. First things first, I need to create a new node based on the value. Then I need to grab a copy of mhead to operate on it. And then I need to check if mhead and else, meaning if it's valid, if it's valid means it's not null, means list is not empty. So if list is not empty, otherwise list is empty. Oops, list is empty. So this is very easy. If the list is empty, then mhead becomes the new node. So L new node. Otherwise, if the list is not empty, which is like this. So I have mhead pointing at this node. And this node, let's say, has the value 10. This node has the value 15. This node has the value 5. So somebody called push front. So I went ahead and create a new node with the new value. Let's say the new value is 20. And the new node is pointing to null. I need to simply say, hey, new node, I don't need you to point to null. I need you to point to whatever mhead is pointing to. And then I need to tell mhead, you no longer point to this node, you now point to this node. So now mhead is pointing at the new node, and the new node is pointing to the existing list. So basically, I pushed this in front. If that doesn't make sense, I'm gonna go ahead and do this like this. And then imagine when someone calls push front, I go ahead and create a new node that points to this node and carries the new value. And then I tell mhead, you no longer point to what you are pointing to, you now point to this node. So if you follow the list, mhead now points to this node, and this node points to the rest of the list. So I basically say, hey, new node, your mnext is no longer null, it's now the current node. And then I tell mhead to become equal to the value of new node. So since new node is a pointer to the new node, I need mhead to be a pointer to the new node. This is a pointer to the new node, and mhead should point to the beginning of the list. So that's basically it. Very simple. Next is delete node. So I need to delete a node on a specific what? On a specific value. So void, oops, no. Actually, let's test it before we move on. So void, my list, delete node takes a double A value. And then there's another one that takes a position, int position. So int a position. Let's go ahead and test push front. Here it is. Push front 1472. So I'm gonna stop here again. At this point, we have 5 nodes. Here they are. 1, 2, 3, 4, 5. And the last one points to null. Then I'm gonna insert 2 nodes. Let's inspect. Okay, so the last one from append was 41. Here it is, 4111. This one. Oh no, I push front. I didn't append. So the first 5 were append, which should start at here. To start at this, I appended. Oh, I can't go back. So here it is. Go back. So again, sorry. Here you go. Boom. So I added these 5, which are 1, 2, 3, 4, 5. And then I called push front 14.1, which worked. 14.4 became the node at the beginning. And then I called push front again, which is 72.89, and it got pushed in front. So my list now looks like this, which is exactly what I wanted. Continue. So the next one is delete node, but I noticed in the test we have insert. So let's do insert. Let's do insert first, and then we can test delete by val, delete by pose, and then display node. Actually, let's grab this whole piece all the way to insert, copy. And then what I can do is I can comment the section that is not implemented yet. So all the way to insert. We can comment this out and save. This is inserting this value at node 4 and this value at node 1 or position 1, sorry, as an insert. And then I need to throw, where does it say? Here it is. Throw a string error if incoming positions values are invalid. Okay, so insert node. Insert node has the prototype as following. So what do I do in insert? In insert, I need to basically traverse until I reach this position. Meaning, as long as this node, as long as current node or current position is less than the targeted position, move forward. So I need to move forward as long as I didn't reach this position. However, as we noticed before, in insert, where's my drawing? So in insert, let's say this is our list so far. As a matter of fact, let's draw our list. Right now, our list looks like this, right? So, how many? 1, 2, 3, 4, 5, 6, 7. So I have 7 nodes. 1, 2, 3, 4, 5, 6, 7. This points to this points to this points to this points to this, etc. The first one is 72.89. So 72.89, 14.44, and then 20 dot, oops, and then 20.5, 2.85. So 20.55, 2.85, 85.42, 85.42, and the last two are 61.28, 61.28, and this one is 41.11. So this is how my linked list looks right now. Let's, I think I can select now. Select like a group, yeah. Yeah, I want to move them a little bit here like this. Perfect. So the first command is insert 3.34 at position 4, and the requirement is to start from position 0. That means this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So the command should insert the node at position 4. That means the new node should come here. 3 points to this, and the new node points to this, and this link becomes destroyed. So this is how the list would look like when we execute the first command. 3.34. 3, oops, 3.34. So as I mentioned, since the targeted position is 4, I need to keep moving forward as long as I didn't reach 4. Once I reach 4, I need to tell the previous node to point at the new node, and then the new node to point at current node. So I'll be at current node 0. It's not it. Current node 1, it's not it. Current node 2, not it. Current node 3, not it. Current node 4 is it. So current node is 4 and current node is 85.42. I need to keep track of the previous node so that I tell previous node to point at the new node and the new node to point at current node. So this is the plan. Let's go ahead and implement it. First things first. My node pointer L new node equals new L my node with a value. Then grab a copy of mhead. I also need a placeholder for previous. So my node asterisk L previous. and we're gonna start L previous as null PTR. And what else? So I'm gonna iterate. Oh, I need an int L current position. It starts from 0. So now back to the basics. I have one out of the two cases. One case is the list is empty. One case is the list is not empty. If M head, else the list is empty. If the list is empty, I can just tell M head to point at the new node. So M head equals new node. List is empty. So if the list is empty and the user says insert at position 5, I can just put it in place of M head. M head at that point will become would be null. So it's no longer null. It's now the new node. Otherwise, if the list is not empty, just like I have it here, as I mentioned, I need to traverse up until I reach position 4, meaning I'm gonna start at 0, and as long as current position is less than the target position. So I'm gonna say while L current position is less than A position, I need to keep moving forward. Let's grab a current node because that's the plan. These are like this current position. I'm just gonna say car position just so it doesn't take space. If that's the case, move forward. So L current node M next equals sorry, L current node equals L current node next. L L current node M next. Okay, perfect. However, I need to keep track of L previous, meaning uh, right before I change L current node, I need to say L previous equals L current node. Yep. And then once I move forward, L current position plus plus. This will move forward. If I let's see, how do I throw? At this point, if this gets assigned, meaning what I'm trying to say is if I reach, let's say my list has 5 nodes, and someone says insert at position 10. Maybe I should do that in here too. What does the requirement say? Be careful all incoming questions that are invalid. For example, negative values you should show. So in case of only in case of negative values. Okay, only in case of negative values. Let's go to the code, meaning if a position is less than 0, then I need to throw string invalid index return. Well, I don't need to return because throw will actually return. Otherwise, if I keep moving forward, and at some point, if L current node becomes null, means I reach the end, L current node equals null PTR, then break. No need to keep going, right? If I, for example, back to the drawing, if I have 6 nodes, eventually this one is pointing to null. So if I'm iterating, well, before I say that, let's say someone calls insert and gives me position 10. So I'm automated, right? I need to traverse up until I reach 10. So if I'm traversing and I reach the end, the last node, I need to stop and insert, or basically append the node. I no need to keep going, or actually I can't keep going. So here, what I'm saying is, give me next. So if next, which is now after this, when this line executes, al current node would be next of current. So if the next was null, then stop. I don't need to continue. Then in this case, I break out of the loop and I can append. Well, instead of appending as a function, I can say L previous, because I have track of previous, right? L previous next equals L new node. This is what I need to do. Dereferencing in also. So I need to take care of that because it might be that this never executed, right? What if a position is 0? What if someone is asking me to insert at 0? Then this loop will never execute. So L previous would be null. So I need to take care of that case. So if L previous equals, if L previous equals null PTR, that's one case, else another case. So one case is somebody called with position equals to 0. So if that's the case, and if someone for whatever reason calls me with position 0, then what I need to do is basically saying that the new node's next equals L current node, which is head and this time. And then I tell the actual M head to start pointing at. So basically I push front. So this case has been taken care of. And then we need to test it. So let's go all the way to here. Start. So when these get executed, my list should look like this. So they are asking me to insert at 1. Insert what? Insert 97.68 at 1, meaning here this would look like this. Let's make it nicer, like this. 97.68. So 97.68. Then this points at this points at this. And this link is destroyed. So my link list should look like this. And let's confirm at this point, my list, quick watch. Boom, 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 boom. So something is wrong. See? I lost my list when I inserted at 1. So let's debug it. Stop. First, let's see if this is the problem or this is the problem. I think this is the problem, but I want you to see it. So before I execute this one, we were attempting to insert at 4. So let's see if it did insert. Here, something is wrong. Okay, so insert in as a whole is wrong. So 72, 14, 20, here it is 20, and then 285, here it is. And then it did insert, so it did insert it, but the link, this link is broken. So it did insert, but mnext is null. So mnext is null. So let's go fix that, meaning when I say, when I break out of the loop. So here I'm chasing it up until I reach the position. Once I reach the position, here, this is what I need. I need L new node M next to be L current node. This is the thing I was missing. I told previous to point at the new node, but I didn't tell new node to point at current node. So this should fix it. Let's confirm. Oops. So quick watch. Boom, 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 boom. So the last thing is 41.11. 41.11, correct. And then 3.34 is the fifth one. So 1, 2, 3, 4, 5. Fifth one. Here it is. And then it's pointing to 85. Pointing to 85. Here it is. Boom. So let's execute the next one. Boom. Oh, it stopped executing. So execute. Let's see now. Boom, 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 boom. So 72 should point to 47. It's not pointing to 47, so something is not right. Oh, well, not 47, 97, sorry. 97. So yeah, it's not, it is actually pointing to 97. And then 97 should point to 14.4. Here it is. And then the list moves on. Continue. Boom. So this is done. Next is what? Delete at specific value, and then delete at specific position. So let's start with delete as on specific value. Here it is. It does not have a member delete. Yeah, it does. Oh, delete node. Okay. Delete node. Delete node. So we need to delete node. Deleting a node should be easy. I need to chase it. I need to traverse up until I reach the value. If the value is what I'm looking for, I need to eliminate. For example, let's say we need to delete 20.55. I start traversing. Hey, are you 20.55? No. Okay. Next. Are you 20.55? No. Okay, next. Hey, are you 20.55? Yes. Okay, since you are what I'm looking for, I need to delete you, and then I need to tell the previous to point to next so that I maintain the link. So let's do that in code. First things first, I need a copy of mhead. As a matter of fact, we need a previous too. We need to tell previous to start pointing to next. So here it is. And then one of two cases. It's either this, else I'm gonna throw. Else I'm gonna throw, because else throw string list is empty. I can't delete from a list is empty. In that case, I'm gonna say traverse. So while L current node is not null, while I have a valid value. While I have a valid value, L current node is not null. Then I'm gonna say, hey, are you what I'm looking for? So I might start at M head, right? Here. I'm gonna start from this. It might be the node I need to delete. So here I will check if L current node M data equals a value. If that's the case, else. So it's either the case or I need to basically move forward. So move forward means L previous equals L current node, and then L current node equals L current node I'm next. I'm reserving previous and moving to next. Then in this case, if it is actually what I'm looking for, if it is what I'm looking for, I have two cases. I have two cases if it is what I'm looking for. It's either the first node, meaning no previous, or one node that has previous. So then the node that I need to delete either has a previous or it doesn't have a previous. How do I know? I know by comparing to head. If current node equals to head, then it doesn't have previous. Otherwise, um, um, otherwise it has a previous. So here I'm gonna say if L current node equals head, that's one case, and this is another case. So in this case, if it is actually head, I'm gonna say a previous will be head because I need to release it, meaning I'm preserving L previous. I'm preserving it, preserve head. Then tell current head to be the next node. So head is L current node next, right? Because basically, if you look at the diagram, let's say this is my list, and then somebody calls and asks to delete 7289. And we know that head points to that node. What do you do? What I do is I need to tell head to point to the next node because this is current. 0 is current. Let's go back. I'm gonna start traversing looking for 7289. Hey, 7289, are you what I'm looking for? Yes. Okay, I need to delete you. Before I delete you, I know you have a next, and I know that you are head. I know that you are head. Based on this statement, you are head. So before I delete you, I'm gonna say that head is reserved. So previous is head. I'm gonna reserve head means I'm gonna reserve a pointer to this current node. Then I'm gonna say, hey head, you become current node, the one I am on next. So current node next. So this statement right here will actually break this link and tell head that you are now pointing at 97.68. The last thing I need to do is delete current node, or I can delete previous because they both are the same. Previous was a pointer to this node, and all current node is a node to this node, is a pointer to this node. So whatever you like, you can do it the way you want. Head is this, and then delete all current node. or you can delete previous. So as a matter of fact, we don't really need to preserve in this case. Head equals next, delete current. Yeah, this is enough. This is way more than enough. In the case that it's not head, in the case that it's not head, I'm gonna undo, 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 undo. So in the case that is not head, for example, we need to delete 25. So I need to traverse. I need to traverse, and while traversing, I need to keep track of previous. Then once I reach what I'm looking for, I'm gonna say, hey, previous, I need you to point to current node next. So L previous next equals, so L previous next equals L current nodes next. And then I delete this one. So L previous M next equals L current node M next. And then delete L current node. And then I'm gonna say L current node equals L previous M next, just to be safe, meaning this would be current node. L previous, which is this, next. So this becomes current node. What's this? Differencing null pointer previous. So previous null if current node, but I am inside the loop. I am inside the loop. And it's not head. You know, I might need to, here I'm setting it. So if it is what I'm looking for, means it is, and it's not the first one. So here I need to keep track of previous. So before I move on, where did I move on in my code? So if, else, here. This should be here too. Because whether it's if or else, L current node, yeah. Yep, I need to, L current node is head. Yeah, so if it is equal, oh, actually, whether it's equal or not, if else. So whether it's equal or not, I need to move forward. This should fix it. It's telling me this is uninitialized, but it is. Here it is. Let's test it. So delete node 61. So let's go to this line. Boom. So delete node 6128. Which one is 6128? Do we not have 6128? Oh, here it is. 61. So fifth. Let's see. Did it delete it? Quick watch. So it was between 85 and 41. So 85 and 41, it did delete it. Here it is. It deleted the 67 and then connected 85 to the 41. Perfect. The next one is to delete on a specific position. Delete node. delete node, it takes an integer. This should throw if they ask us to delete in a wrong spot. So delete node on uh, value and delete node on a position. It's similar, by the way. It's very similar because I need to do the same. Hey, did I reach the position or not yet, etc. So let's grab this. And then I need one more, which is L current pose. One of the two cases, if I'm head, else. Else I'm gonna throw. I'm gonna say list is empty. Yeah. Now if it is not empty, I'm gonna say while L current position, similar to the insert. Remember the insert is a position. First thing is current position increment before we forget. Come on, L current position plus plus. So while I'm iterating, boom, 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 I'm gonna keep track of previous for sure, and basically move on. So I'm gonna move on, just move on. So L current node equals, oh, before I change L current node, let's grab a copy of it, and then L current node becomes L current nodes M next. And similar to insert, right when I do this step, I need to check if I am at the end, if I reach the end. So if all current node equals null PTR, then then throw. Um, Position out of range. Because this is the case, all current node equal to null pointer. Okay, let's put it behind before it then. Now I won't be referencing a null because if it is a null, the code will terminate. So boom, 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 boom. We keep a previous. Let's move this code here just so it looks nicer, better code readability. So this is here. I'm keeping track of previous. Boom, boom, boom. Okay. So once I break out of this loop, I have one of two cases, right? When I break out, I'm traversing. I'm traversing and I'm looking for a position. I'm traversing and I'm looking for a position. It might be this position, or it might be any other position. So it either has a previous and I need to delete and make a connection. Basically, sorry. It either doesn't have a previous and I just need to delete and tell mhead to point, or it does have a previous and I need to make extra code to connect previous to next. Similar to delete by value, but now the criteria is we found a value. We found a position instead of we found a value. So just exact same. Where did we do something like this? See, if I'm head or not. But following what we are on right now, I break out of the loop, means I reached what I'm looking for. I either have L current node equals M head, right? Meaning it is the first node, else. So if it is the first node, I'm gonna say, hey, M head. If it is actually the first node, I'm gonna say, hey, M head, I need you to point to next because L current node is the first node and it needs to be deleted. Then I'm gonna delete L current node and then I'm gonna return done, deleted. Else you are not the first node. So L previous am next equals L current nodes am next, and then delete L current node, and then return. Finally, return. This is it. This is it. Let's test it. This should throw, and this should delete. So let's start all the way here. What do we have on 2? So on 2, we have, this is 1, this is 0, I mean, 1, 2. So we have the 14.4. So let's hit it, boom. So it's 14.4 should be gone. Here it is, it's gone. Yep. So it deleted 14 and it maintained the connection. Perfect. Now this should throw. Perfect. Position out of range. Very good, very good. Display node. Display is simple because we know how to traverse. Oh, display node. Not display all list. Display node at this position. So kind of similar, but there is no extra code because I'm only gonna display. So there's no like deletion and maintaining of the connection. I'm looking for a position. Once I see it, I display and that's it. So display node has this void, void my list display node. So basically, I'm gonna traverse. So let's grab a copy. First things first. Grab a copy of mhead. And then I'm gonna traverse while al current position less than int, sorry, a position. So let's keep a track of al current position equals 0. Yep. Mm, 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 mm. Then if similar to what we did, if L current node equals null PTR, that means I'm out of range and I need to throw string position out of range. Yep. Otherwise, move forward, meaning L current node equals L current node. I'm next. Yep. L current position, sorry, whoops. Yeah, this looks nice. And then when I break out of this loop, I'm for sure on the uh, node that I'm looking for. So I'm gonna say L current node data. Yeah, let's test it. Display node at position out of range. Here it is. Perfect. Let's see. Mhm. Now I have all these new lines for no reason. Okay, so display node, here it is. Boom. Display node at position 30, it's through. Perfect. How about, oh, sorry. How about display node number 1? Here it is. Boom. Perfect. Insert at 1. Okay, so now display node at position 7. Oh, okay. I had it already. So 1 will throw and 1 will display. And then what else? Display, destroy. Okay. Display list. So display list should be straightforward as well. I need to iterate my linked list and display on each node. So display list, first things first, give me a copy, then while L current nodes next is not null PTR, then cout L current node data space comma maybe whatever or end line, then move forward. L current node next. Yeah, this is display this as simple as that. Now for this try list, I need to traverse and keep track of previous. Once I move forward, delete previous. So let me grab a copy of this. However you want to think about it. You can keep track of previous or you can keep track of current, move to next, or reserve, for example, next, delete. So however you want to think about it, as long as you achieve the goal, which is deleting each of the nodes, not just the first node, not just delete amhead. You need to iterate or traverse and delete all the nodes one at a time. So let's keep track of my node asterisk L next. We can keep track of L next. At this point, it is null, while L current node is not null. I'm gonna say reserve next. So L current node next. Delete L current node, and then L current node is whatever I preserved. This is basically it. And then the constructor can actually call destroy list. So if I start, I started without debugging. So start. So something is wrong in display node. What's wrong? So this is null and I'm trying to access it. Let's see. L current node is null. Otherwise, maybe I can display here. I can display before I move forward. So now L list should be destroyed. So amhead has been destroyed. What I can do last thing before I destroy list is set amhead to null PTR. This is important. I missed that. I confirmed that the amhead was actually deleted because of the junk values we saw. So each of the node has been deleted, released back to the memory, but amhead as a variable was still pointing to something. So I deleted amhead, so now amhead is null. This will allow me to check if the list is empty. Because if you recall, all our checks in the previous methods to check if the list is empty is by checking mhead. If mhead is null, then the list is empty. So it's important when I destroy the list to set mhead to be null. Otherwise, all my previous checking will have misbehavior. So this is it for chapter 18. Let me know if you have any questions and good luck.